Hello and welcome to the next episode of EVM and Yule programming course. This is finally time to go through Yule programming language. Everything what was there to know about EVM is already covered. So if you haven't checked that out yet, please go back. The EVM course is in the same playlist. Just play the first video. Start with that, and when you are done with EVM, come back here and then we will start to learn about Yule. In this episode, I would like to introduce you to Yule programming language, and as with EVM, I would quickly go through the main things to know about this language. So let's move on. First, what is Yule? Yule, also called Julia, is an intermediate language that is compiled to EVM bytecode, to opcodes. Currently, it is used as intermediate representation of Solidity, which means that compiling Solidity to EVM is a two-step process. And the first part, Solidity, is compiled down to Yule programming language, and only then Yule is compiled to EVM. You may ask, why even bother doing that? This adds up complexity to the process. Well, of course it does. However, on the other hand, it allows to simpler optimizations. Many programming languages are using LLVM, which is a suite of tools for compiling languages. It was initially created for C or C++ language. Due to its design, many languages are actually using that. So how LLVM works in short is it compiles the code first to its internal representation that is similar to assembly, yet on level that is one level above from the machine code, and this reduces the complexity of the code, because in normal programming language you may have multiple if instructions, multiple for loops, and all these different possible ways in which developers may use the language that may be hard to predict and may be hard to improve upon, because then you would have to predict and write optimization code for all of these different cases. And having simple intermediate language allows you to simplify those steps. Next, apart from using it as intermediate representation, you can write Yule yourself, either via embedding it into your code in assembly blocks, or you can write standalone Yule program that will have no notion of Solidity inside. We will cover both of these cases later. And now let's go through some more important virtues of the language. Starting out, Yule has only one data type. This is the 256 bits or 32 bytes, just as EVM has. The difference here is if you are embedding Yule into your Solidity code, you can reuse variables of different types here. However, in Yule, they are still uint 256 or bytes 32. Next up, just as with EVM, you have manual memory and storage management. Good news is that you have some helpers that are useful. So in case of memory, those are helpers provided by Solidity language. And this is the model of memory that Solidity language uses. And if you want to embed your Yule code into Solidity, you have to know about it. We'll go through that. And concerning storage, each storage variable has both slot parameter and offset parameter. Those are really useful because now you don't need to know which variable has which storage slot. but you can dynamically use storage variable dot slot or storage variable dot offset in case if this storage variable is not full bytes 32 and may occupy, you know, just a part of the storage slot. So Yule gives you this ability, which is super cool. Next, you don't have ABI encode and ABI decode. This is only Solidity thing, and actually this is just a helper that takes bytes and slices them out into small variables that you can use later. Next up, you cannot use stack operations. Even if you want to, normally you cannot do that. There's only one operation that you can use. This is pop, which just takes an element from the stack. This is used only in cases when you have some expression that returns something to the stack and you don't need that. For example, if you are performing low-level call and low-level call returns you status of the call, whether it was successful or not. If you don't want this result, if you don't need it, you can wrap this call inside pop and then it will be discarded. But this is the only operation that you can use. However, there is verbatim, and verbatim allows you to actually inject any bytecode that you want. Okay, so in case of verbatim, you can see you can pass any opcode here. In this case, we have push 1, number 2, and multiplication. So we are multiplying this x by 2, and verbatim always is defined like that. It's verbatim underscore how much input parameters we have. In this case, it's 1. We are taking x here. And how much parameters out we have. In this case, this is also 1. Because we are first pushing 1, we are pushing number 2, and then we are multiplying this number by 2. And this will return to us, in this case, a double. So this will return the stack value that is there, that is returned from this operation. However, you should really watch out for verbatim, because it may really mess up all the surrounding code. Because remember, call stack memory is reused by all other parts of the code. So if you do any change, it may negatively impact other parts of the code in really unpredictable ways. Next up, you can either use Yule either standalone or embedded into Solidity. So this is excerpt from Yule documentation, from Solidity documentation. And you can see here that we have normal functions from Solidity. Part of the function here is written in Solidity, and part inside is written in pure assembly. You can see that it returns some, and we actually can reuse the same parameter inside of Yule, which is super cool, because we now have this hybrid that we could perform part of the calculations inside of Solidity, and in the parts when we really need to dig down into opcodes, we can then, reuse, take this variable and take it from there. And finally, we have function in pure assembly. So you can see that we are loading the length of data, because in short, we will go deeper into that. If you have unbounded arrays that you don't know the size of, first parameter, like first element of the array, is actually its length. It's always like that. So here in this function, we have the data, which is unbounded array of units, and it's stored in memory. So if we are loading data, and so actually pointer types, which are arrays, which are, for example, storage variables, in assembly just denote at which position they are. So in this case, data is not really the data passed here. This is the number at which in memory the data is located. So if we are loading data, we are actually loading the, so we are first getting length of the array, then we are adding 20 in hex. So this is actually 32 because we have 32 bytes. So data element location will be updated each time, but it denotes a current offset of the element that we want to sum. And then we have for loop, which looks a bit differently than in Solidity. The for loop has 3 elements. It's very similar to how it works in Solidity. So first you are defining your variables that will be used in loop. Secondly, you are defining the terminal condition that if met stops the loop. And finally, you are denoting what has to happen with each iterations with the variables. So in this case, we are incrementing data element location until this is equal to end, and our end is just initial location with length multiplied by 32 bytes. So we are going through the chunks of 32 bytes, and if we are moving past the last element of the array, we are finishing the loop. So this was example of Yule embedded into Solidity, and now some example of standalone Yule. So the main element in standalone Yule is object. You can give it, actually you have to give it a name. An object may have side or may have another object. If you haven't seen that before, it may seem really strange, but what it really does, first you are defining the constructor, the code that will construct this contract. So in this case, we are assigning to the storage slot 0 caller in Yule is message.sender, and then we are deploying the contract. So what we do to deploy the contract, first we are doing data copy. Data copy just copies everything from given object, and that's why we need names for objects. In this case, we are copying all this object runtime. So data copy first sets the offset to which copy given data. Then you have to pass from what data offset you want to copy it from, and then what is the size. In this case, we are just copying everything that is in this runtime object, and our runtime object is actually the deployed contract. Finally, as you know already from the bonus episode of GAF, we are returning what memory part to deploy to the chain here. And this is our runtime object, and it has code, and you know, this code is actually the smart contract. A trivia right now, first of all, this is requiring that you cannot send ether to it. Solidity does that for you. Then you have function dispatcher. So if you have multiple functions in your smart contract, Solidity automatically adds similar code to that. It checks first 4 bytes of the selector. Like, for example, it takes catch-up of balance of address. It creates a catch-up of it, and it checks first 4 bytes if they match. So now, depending on the selector that it matches, it goes through the specific function. And you can see here that function definition is very similar to the definition of solidity. The biggest difference from definition of solid function is that it does not use the return to signify that this function returns something. It uses this arrow to signify that it returns something. So in this case, we are returning R, and R is the result of this equation of checking if A greater than B is non-zero, which in simple words means that if A is greater than B, if this is true, it will return 1. And we are checking if this is 0. So it will only be 0 if this is false. So if A is not greater than 0, that is either lower than or equal to B. So this is why we have this function defined like that. Next, instructions are named after EVM code. So for example, we have stop, add, mod, exponential, stores, sload, tload. So with high dose of certainty, if you know EVM, you can tell what the UL name for a given operation will be, because UL in most cases just takes the EVM opcode name. So it's easy to, if you actually know EVM and have a slight understanding of how UL is constructed, then you basically know like 90% of UL programming language. And last thing about UL is that UL is expression language. What does that mean? First, let's go through what is statement and what is expression. So I prepared this small code chunk for you to see the difference between statement and expression. So what is statement? Statement is just stating what something is. In this case, for example, we are stating that our x has value of 5. Next, we have statement of function execution. Then we have our expression that returns something. Function retrieve gives us back some value. So this is an expression that we can then use to assign it to number y. And this gets even crazier because, for example, assigning a number to another one is also an expression in Solidity, at least, because it returns a value. So if you have some number x and you assign to it incremented value of y, so y is function retrieve and it takes the number. So because we set it before to a, it should be 9. You can see in logs that it is really 9. But most important thing here is that you can actually use this, and because this is expression, it returns some value, and you can then use the result of this expression for your statement or other expressions. So having said that, now everything in UL is an expression, what means that you can stack multiple UL expressions inside another UL expressions. And we actually saw that before. In this case, for example, we have greater than, which is expression. That means that it returns some value. And then we use the result of that expression into E0 expression, which also returns some value that we use here. And you can see here that we can chain it even more. We have two lower than operations which are chained into OR, and it may get really, really crazy. You may nest it multiple and multiple times. Of course, there is issue of readability, but technically just you can do that. So this is the end of the first episode. This was just a brief introduction to the UL programming course and how UL looks like. In the next episode, we'll look into some basic operations and the stuff that will help you out to understand Yule better. See ya.